Chapter 1, Digital Systems and Information, Ranges for Number System Representation. In this lecture, we will learn how to determine the number of unique combinations that can be represented based on the number of bits available in a system. We will then turn it around to determine the number of bits required to represent a unique number. Our objective for this lecture is to understand and recognize range of representable numbers given an n-bit system. In digital computer systems, the range of numbers that can be represented is based on the number of bits available in the hardware structures that store and process information. The binary number system is the most natural one for a computer. Therefore, the number of bits in these structures is typically a power of 2, such as an 8-bit system, a 16-bit system, a 32-bit system, or a 64-bit system. The number of values, combinations, or permutations that can be handled by a binary system with n bits is 2 to the n. The range of unique values that could be represented is 0 to 2 to the n minus 1. No two elements can have the same value. Otherwise, the code assignment will be ambiguous. So a 1-bit system would have 2 to the 1 or 2 unique combinations, which are 0 and 1. A 2-bit system would have 2 to the 2 or 4 unique combinations and can represent 4 distinct values, 0, 1, 2, and 3. Up to this point, the ranges we have demonstrated relate well to unsigned integers or non-negative numbers. To represent an unsigned fraction with a binary point to the left of the most significant digit, the range of fractions would be from 0 to 2 to the 16 minus 1 divided by 2 to the 16 for a 16-bit system. In later chapters, we will deal with fixed-bit representations and ranges for binary signed numbers and floating point numbers. In both of these cases, some bits are used to represent information other than simple integer or fraction values. How many unique values can be represented by a 4-bit system? Our n value for this system is 4, which means our system could have 2 to the 4 or 16 unique combinations. The values that are represented by the system would be 0 to 15. And 15 is 2 to the 4 minus 1. So, if n is equal to 1, or 2 distinct values can be represented, such as unsigned integers 0 and 1. If n is equal to 2, 4 distinct values can be represented, which range from 0 to 3, so 0, 1, 2, or 3. If n is equal to 3, 8 distinct values are represented, and they will range from 0 to 7. So 0, 1, 2, 3, 4, 5, 6, and 7 are represented by a 3-bit system. If our system is a 4-bit system, 16 distinct values can be represented, which will range from 0 to 15. A 5-bit system would have 32 distinct values represented, from 0 to 31. A 6-bit system would have 64 distinct values represented, which range from 0 to 63. A 7-bit system would have 128 distinct values represented, which range from numbers 0 to 127. An 8-bit system could have 256 distinct values represented, and those values would be 0 to 255. How many bits do we need to represent 48 unique elements? A 5-bit system can represent 32 unique elements. A 6-bit system can represent 64 unique elements. So the number of bits we need is in between a 5-bit system or a 6-bit system. In order to represent 48 unique elements, we would have to go with the 6-bit system. Note that not all 6 bits would be required. So we will have unassigned bit combinations, which means that leading or trailing zeros would be necessary. How many bits do we need to represent the number 48? First, determine the range that contains the number 48. Let's start with a 5-bit system, which can represent the range of numbers 0 to 31. 48 is greater than 31, therefore a 5-bit system is too small to represent the number 48. A 6-bit system can represent numbers 0 to 63, so our system would require a 6-bit system. In summary, the range of representable numbers have been computed and the number of unique combinations found. And that concludes this lecture.